Hello, everyone. Good morning. Welcome to the second day of Ignite. My name is Pablo Castro, and I work in the Azure AI Search team. Yesterday, we heard a ton about agents and the Copilot stack. Now, these applications are only as useful as the data they front. Ultimately, when we build business applications or applications for our end users, what we're looking for is how do we connect the reasoning capabilities of language models with the information that is the most important for our business or our application, whatever is the goal that we're managing. Now, in that context, in this session, we're going to talk about Azure AI Search and its role as an information retrieval system. The retrieval system is the piece of the equation that can connect language models to your data to create these agents or these Copilot systems that connect your users with the answers that they need to go about their business or to use your applications. So what we'll do today is we'll talk about how, with Azure AI Search, you can get the best results for the RAG pattern, for the retrieval augmented generation pattern. Then we'll talk about how to do that at all scales. And then third, I want to walk you through some use cases for how this can be done across a variety of scenarios, no matter where you're working, from Visual Studio to Copilot Studio to anywhere in between. Just as by means of a very quick recap, when we talk about retrieval augmented generation, we talk about this kind of primary pattern these days to connect data with language models. Usually, you have a piece of orchestration code in the middle. Now we call them, like they evolved into agents because initially they were this very simple, way back, say, a year ago. This was very simple orchestration systems that would call the language model and the retrieval systems. We've learned a lot since then. Newer systems use this agentic approach where you iterate over a task and you pursue the goal. And in the end, you're still brokering interactions between the language model and the retrieval system. So on one hand, there is a language model that's your engine of reasoning. On the other hand, the retrieval system is what glues together the retrieval system with data. And what that means is there are two critical elements that you need to look into in order to have a retrieval system that would do its job well. First is indexing. What do you need to do to your data so it's in the right shape to power your right application? And the other one is retrieval. Or how do you find the best pieces of information that are needed to answer any particular question? Now, what we do in the context of Azure AI Search is we look at this as a kind of whole stack problem, where we start on indexing and how we prepare the data, and then we go through query pre-processing to the recall stage, where we find all the candidates, to re-ranking, where we find the best out of this pool to answer a particular question, and eventually into answer synthesis, and how do we best present this to users. During this session, what I'm going to do is walk you through a number of new innovations we've made in this space to make it easier to build better and faster applications that are powered by the RAG pattern. Now, we're going to start with better results. Better results are critical for RAG. Ultimately, the application, the language model, can only answer questions that are as good as the grounding data you feed it. So much so that the LangChain folks did this survey just not that long ago. They talked to over 1,300 people. And one of their questions was, what is your biggest limitation of putting more agents in production? By far, the #1 concern people have is the performance quality of these systems. Like, are they answering the questions correctly? And the challenge with this is these systems look so confident that people can overtrust them without the right metric. So it's critical for us to create a system that has high quality, that is carefully measured, and is well understood how it works to make sure that we get the right results for every question our users ask. So because quality is so important, in Azure AI Search, we invest a ton of energy on making sure you get the best relevance out of search results right out of the box. And today, I'm very excited to talk about our generative query engine. This represents the best work that Microsoft has done at the platform level for relevance. It includes query rewriting that we're powering by SLMs, a brand new, massively better ranking model, and all of that packaged in a high-performance system that would not make you trade off quality for speed or speed for quality. So let's dig into the details of this generative query engine. If you look at some of the slide, some of the columns of the slide I had a couple of slides ago, it showed kind of what we go through when you run a search in Azure AI Search, or in any kind of sophisticated search system for that matter. First, we go through query preprocessing, then we retrieve candidates, then we rank, and then we produce an answer. A typical way to do this is to do just vector search. We've seen that that doesn't work very well in every scenario. We also have keyword search, has its strengths, but also has its weak sides. We've found that hybrid retrieval is a reasonable baseline. So that's why you see this branch where, on one hand, we take care of vectorization and vector search. On the other hand, we do kind of symbolic NLP-style manipulation of the content. And then we do keyword search. Then we fuse the results together, re-rank them to find the best candidates. And finally, either we feed the results to an LLM to produce an answer, or Azure Search can, right out of the box, do extractive answers and also query contextualized captions, if that's what you're looking for. So these two components I mentioned before fit in the stack this way. First, we have a brand new semantic ranking stack that is specifically tuned for RAG scenarios. We've learned a lot about how RAG applications are built and what do they look like, what the data that is powers them look like, and we've used all of that to build a new ranker that boosts results across the board on a variety of data sets and query types and whatnot. We also are introducing a new query rewriting stage that runs early before we go deep into the recall phase. What this allows us to do is to improve on hard queries. While the re-ranking system allows us to lift all cases, there are ultimately cases where if we can't find the initial good candidates among all the data in your data set, then there's nothing the re-ranker can do because the right pieces of information are simply not there. Query rewriting helps us find the right initial candidates that then we can re-rank. Let's look into these two in more detail. So first, I'm going to talk about the new L2 re-ranker. About a year and a half ago or so, we shipped an initial generation re-ranker. And that re-ranker had already boosted, for the majority of the scenarios, by a significant amount, the quality of results you get in Azure AI Search, just out of the box by enabling it. So I'm excited to see the massive amount of progress the team has made in this regard. We are up 22 points from our baseline in NDCG, which is a common metric that is used in information retrieval. This is a significant improvement, both from our last year's model and also from what is the baseline for relevance. These days, we no longer compare vectors alone or keywords alone. That baseline is just not acceptable. We've been using hybrid as a baseline. That at least is a little stronger than the two combined. In general, hybrid retrieval alone is not going to do it, but it represents a good starting point where we can build from. You can see in the screen how much better even our old model was on top of hybrid retrieval, and you can see our new model, how much far out is right now. So a few things we did to make this work is we looked at what does the data look for current RAG applications. The advantage we have this year compared to last year is a ton of RAG-based applications have gone to production. So we see what the real data looks like, and we can adapt our ranking system, how we train, how we architect the ranking neural network and whatnot to fit the specifics of this scenario. So for example, one thing we learned is what is the chunk length distribution, like what is the typical documents we have to re-rank. And we adjusted the context window of the re-ranker to fit the vast majority of these chunks entirely. So that means we don't have to do summarization steps that both affect performance but also lose information. So we made the kind of context window of the re-ranker about 8 times wider, and that allowed us to fit, again, in nearly all cases, we can fit the whole chunk in the re-ranker. That means we don't lose any information, and we don't take any extra steps to get the re-ranking done. The other thing that I'm super impressed that the team pulled off is this comes at no performance trade-off. So you get a consistently better ranking results across the board, across a variety of data sets, and the thing is actually faster. This is a combination of using modern techniques and how we organize the actual re-ranking model combined with a number of optimizations. Because in the end, the ranking model itself is actually larger. What we find is in very small chunk lengths, say in the 100 or so sizes, we more or less have the same performance we had before. But in the most common kind of chunk length range, say like in the ballpark of 500, maybe to under 1,000, we can be up to over 2 times faster than the previous one in the ranking stage. So what that means is you can get the best in terms of results, quality, and you'll get faster performance from the re-ranking stage than you got before. I also mentioned query rewriting. So what the purpose of query rewriting is sometimes how you formulate a phrase or a question has significant influence on your ability to find the right candidates to then feed to the language model. So right now, the starting capability of query rewriting is what we call paraphrasing, where you should take a question or a query and you reformulate it in multiple ways. This creates a significant improvement opportunity for the cases where you have a difficult query, where you have bad recall, meaning you don't find good candidates. The other interesting thing about rewriting is if you already have a non-vector index, a keyword search index in Azure Search, and you don't want to deal with adding vector support to it, query rewriting actually helps boost this in similar ways to what vectors do by kind of looking for different ways to say the same thing. And you just have to enable it. This is not a size of data operations. This is just a query time operation. You can just turn on or off. You can see an example on the screen of what it does, where I searched for, in this case, I searched the Microsoft, the Azure documentation for data ingestion in Azure Search. And you can see all the different variations of it, where you try different ordering of words, you try different synonyms and whatnot. This is also interesting for us because it's the first scenario where we inlined a small language model within our query pipeline. As you can imagine, we have a very tight latency budget in that part of the stack. So we did a lot of work to pick a very small, small by modern standards, billion parameter model for re-ranking and for rewriting, and we tuned it for this particular scenario and for the speed that we're looking for. Because sometimes you may not understand why you get the results that you're getting. We also introduced a debug mode so you can see what's going on. Well, let me show you these two things real quick in action. So I have a search service here, and I have kind of all the products catalog that Seth was using in keynotes and whatnot. And so I wanted to show you two things. So this is like a product catalog for outdoors gear company. So I'm going to ask how big is the Adventurer Pro backpack. So a few things to notice. First, I'm doing this in the Azure portal, so I had already created the index. You usually do this in your application, but this is a nice place where you can try queries out. And you can see the responses, the candidate documents here. But I want to show you two things in a little bit more detail. So I'm going to open the query in the JSON view. So this is what your application would produce when you formulate a query, where this is the search I did. Second, this is the vector side of the search. You can see there is no vector in the vector search. This is because you can query the Azure Search vector stack with a vector, like you would expect. But you can also just send us the text and tell us to deal with vectorization. So that way, your application is fully separated from the vector encoder. We deal with connecting with it and whatnot. And also, I enabled query rewrites here, and I enabled semantic ranking. So in the context of the two capabilities we just talked about, two things I want to highlight is first, all the value that I talked about in terms of enabling re-ranking, better quality, and whatnot, they boil down to saying query type equals semantic. So it's almost boring to demo, because the only thing you do is you switch this on, and it'll just work. Then, of course, you have to evaluate that it works well for your scenario, but the mechanics of turning this on are trivial. In this case, I also have rewrites turned on. You can see it here. And one thing I can do, so we can see this in action, is I'm going to say debug, and then say query rewrite. So I get debug output for the query rewrites part. And you can see here that now I have the original input query, but also I have all the paraphrasing that the system did for us. And you can see, it tries things like, well, what is the weight? What are the dimensions? What are the size details? So effectively, what it's trying to do is create multiple interpretations and multiple formulations of the same question to maximize the chances that we find the right information. Once we find it, then the re-ranker will find the optimal order for it, and then hopefully the top few of these will contain the right answer that we can feed into the language model. Whoops. So then the question is it good? Like, lots of words about network architecture and SLMs and whatnot. In the end, one challenge we have right now is that there is so much hype. Every week, there is another approach to RAG, there is another approach to retrieval and whatnot. And it's very hard to tell, because they all sound like a good idea. So we've spent a ton of energy on formal evaluations to make sure that by the time we put something in the product, it'll work well, and we understand its characteristics, its quality profile. So evaluations really help with hype resistance, and we take it very seriously. We measure every layer of the stack, and we measure it across many dimensions. So we look at many number walls like this. Don't worry, I'm not going to drain this one. But we look at many walls of numbers like this. And just to give you a sense of how much goes into this, each one of these columns is not, we call it odd data set, but it's actually, each one of them is made of multiple data sets. So we do evaluations extensively on many, many views of the system. So let's dig into a few slices of this to see what it looks like. So first thing we noticed is, there are well-known academic benchmarks for information retrieval. Like BEER is a very popular one. BEER is awesome if you work on search, because it has different data sets. It's very heterogeneous, so you can try different scenarios and whatnot. But it's built for search. It's not built for RAG. So one of the things we noticed is we kept working on making our numbers better, because we're using BEER alone as a reference, and actual customer scenarios weren't improving. And so the reality is that customer scenarios today, our applications powered by RAG, just look different than that data set. We still measure things like BEER and Miracle, because it helps us compare with other rankers and things like that. But we spent a ton of energy building our own data sets that reflect more what we see that you as developers are building in this space. So what we have, thanks to that work, is like a particularly strong increase in performance when it comes to real-world applications, real-world data sets. We see anywhere between 33 and 53% improvement in quality, as measured in this case by NDCG, when you use semantic ranking and query rewriting on top of real-world data sets. This spans customer data sets. Of course, we never train or evaluate on customer data, but we have agreements with some of our customers that allow us to do this, and then support cases and a number of other real-world data sets we've collected. So we're very excited to see that from hybrid all the way to the semantic re-ranker plus QR, we see a massive improvement on quality. And this is one of the cases where I feel we accomplished what we set out to do, which is shift complexity from you to us. So now we deal with this re-ranking problem, and then you understand your business problem better, so you can focus on the business problem side of things. To unpack because sometimes we say, hey, 53% better, like 53% of what in what use case. So I want to give you a sense of how much detail goes into this. In this case, this is just one of the data sets, the multi-industry, multilingual data set. And you can see that in this one, we scan across 10 industries and 7 different languages, and we evaluate all of them. And you can see consistently how much of a boost we see. Like on average, we see 21 points of NDCG up. And this is also true across all kinds of query types, from acronyms and code words to concept-seeking queries and web-like queries and everything in between. So we put a ton of energy to make sure that no matter what your data or scenario looks like, you get a strong baseline profile out of our system. Now, I talked a lot about the challenge of ranking and relevance on the outside of the system at query time. Of course, in many cases, our ability to do a good job on the query side depends on how well the data is prepared in order to index it, such that the access patterns of RAG applications work well. So a typical thing we do on this is if your documents are of any kind of real-world length, is you have to chunk them up. Today, I'm excited to announce that in addition to traditional kind of chunking methods that we've had for a long time, we also support right out of the box structured aware chunking, where we chunk with awareness. So we split the document with awareness of the structure and layout of the document. We do this by integrating Azure AI Search directly with Azure Document Intelligence, so we can take advantage of all the improvements that we've made in Document Intelligence right there in Azure AI Search without you having to coordinate and putting these pieces together. Because layout is so important, even for cases where you may not be using Document Intelligence, we also wanted you to be able to exploit structure. So if you have plain Markdown files and not only PDFs or Office documents, you can treat plain Markdown files as text, but then you miss out on the structure. So we introduced also a Markdown parsing mode so that you can drive the kind of chunking process through this with awareness of structure. So we can split out the headings, can use the headings as boundaries, and even lift heading information. And this is, again, something you have to set up when you were setting up your system, and then we'll do all the orchestration to continuously index documents and run them through this stack. Let me just real quick point you at where you'll find this. So I have another search service here. So in Azure AI Search, the easiest way to start indexing data from scratch and vectorizing and all of that is in the Azure portal, you can go to import and vectorize data. We support a ton of data sources, including Fabric, through OneLake, blob storage, SQL, Cosmos DB, and whatnot. And then now, when you go to one of the unstructured data sources, you'll see that there is an option to enable layout detection. And you have to say yes, that you're OK that we'll use Document Intelligence for this. And after you configure this, then we will use, instead of our built-in engine for document parsing and whatnot, we'll use Document Intelligence for that. The other thing I wanted to show you real quick, I need to change services for this, is if you have Markdown content, and you don't need Document Intelligence, you just want the Markdown structure. So now you can, oops. Oh, I'll make it show up in a second. So now you can select from this list, in addition to text and default and whatnot for parsing modes, you can select Markdown. And when you select Markdown, we honor the heading structure of the document during parsing. Let me actually show you this, show you the output of this in action. So we had like this backpack search before, so I'm going to just do it again. And if we look at the results, you can see now that the results have a few fields, like they have the actual chunk of text, they have a title. But now, in this case, we configured it to extract 3 layers of headers. So basically, the headings of the document dictate the structure of the document and tell us a lot about it. We can use it as chunk boundaries, and we can also extract the actual headings and actually have in separate fields, like I have them here, or have them be part of what you then vectorize or search for. So this greatly helps, especially when you have long pieces of text that they lose context. So you want to have the heading information carried over from chunk to chunk. And now Azure AI Search will just do all of that right out of the box without having you to deal with it. All right, so we talked a lot about quality. How about scale? One thing we've seen is some aspects of retrieval, in particular when it comes to traditional methods like keyword search and whatnot, we know how to scale them. They've been around for a long time, and it just so happens that the nature of the approaches we use to do this at scale are kind of friendly to storage hierarchies and things like that, so we can do it easily. Vector search is a different matter, though. First, while it's been around for a while, the pressure to scale and for cost efficiency has been new for the last couple of years. And second, it's a workload that is particularly tricky to scale cost effectively. So we've done a lot of work to make sure that you get the best cost-effective solution without sacrificing any of the quality aspects that you want to get from vector search. One of the things we've worked a ton on is on vector compression. Now, I'm going to go into a bunch of detail, but you can think of this in two ways. One is, you don't really need to know about this if you don't want to. You can just turn on a set of things, and you'll get all the quality of the original vectors at a multiple times lower cost equation. Now, if you do want to know, we want to give you control. Let me give you a concrete example. So let's say you have 1 million vectors, and you use OpenAI's text embedding 3 large model, which uses 3,072 dimensional vectors. So if you take 1 million vectors times 3072 times 4 bytes per dimension, that's a 32-bit float. So you need 11 gigs of the data without accounting for the data structure overhead. So no matter what strategy for indexing you use, if you need to hold them in memory, you need 11 gigs of RAM to hold per million vectors. So there is a set of techniques that we support right out of the box in AI search that allows you to apply compression to this to effectively use less space. First, there is MRL for vector prefixes. MRL stands for Matryoshka Representation Learning, and it's a technique where you train the embedding such that when you obtain a vector, you can take a prefix of the vector, and the majority of the information is concentrated towards the front of the vector. So if you take a prefix, you don't lose as much. And it works surprisingly well. The other thing you can do is quantization. Quantization refers to kind of losing precision on purpose on each of the elements of the vectors, or maybe the dimensions of the vector. One combination that we found that works surprisingly well is use MRL to take a prefix, say 1024 out of the 3072, the first third of the vector, and then apply binary quantization. Binary quantization, what it does is, for every 32-bit float, it takes 1 bit. And intuition is like, that's not going to work. But I'll show you the numbers. So if you do these two things, then you start with 1 million vectors. Now, we took only 1/3 of the dimensions, so 3072 divided by 3. And then each dimension is 1/8 of a byte, because it's 1 bit. So now we're using 122 megs of RAM per million vectors. So that's a 96x increase in density. Of course, I'm talking about the pure vector data. Then you have to build some data structure around it, and it has some overhead, so you have to kind of account for that. But that's a massive, massive gains in terms of how many vectors you can fit per unit of memory, which in the end translates to unit of cost. Now, of course, when you do this, something has to give. So what gives is you see the quality of results suffer. Like recall will go down, or if you compare outcomes to outcomes, say with NDCG, you'll see them go down by several points. You can get kind of into the low 90s percentage-wise for this. But we have one more trick that we can apply to this. So the important thing is, like, for performance reasons, we want to keep a vector graph in memory or some data structure in memory. But that doesn't mean that we can't stash the rest of the information somewhere else. So in AI search, you can now tell us, what would you prefer? You can say, I want the absolutely smallest thing. I don't want to use memory or disk or anything. And we will do that, and then we'll lose some of the precision. Or you can say, preserve full precision vectors on disk. And then what we'll do is we'll do this tiered approach, where we have a very compact, high-performance view of the vectors in memory. And then we have full precision on disk that we can use to rescore the top candidates. So usually the pattern is, if you ask us for, say, top 5 vectors, then of the 5, we'll query deep, so to speak. What that means is maybe we'll take 10 or 15 instead of 5, and then grab the full resolution versions of these vectors and rescore them at full resolution. So that gives you a sense of how much options you have here. Of course, again, you can ignore all of these and just turn it on, and it'll be good. But as your application gets sophisticated, you want to have this kind of optionality. So this visual gives you a sense of the different sizes, starting from the left for full resolution vectors against per million documents for this scenario, to 8-bit quantization to 1-bit quantization, and then 1 bit plus kind of vector prefixes. And these last two are the same because using this full resolution vector for rescoring doesn't actually use any memory. That's an on-disk operation. So it doesn't add anything at indexing time. It's just a query time trick. Now, quality-wise, this is what this looks like. So of course, as you're increasing your compression level, these are lossy compression methods, so they lose quality. Now, when you combine all the compression methods with oversampling, you can recover pretty much all the quality backup. In this case, it says oversampling at 2x, meaning we query twice the documents you asked. This is a dynamic parameter. You can say some queries, you can say 2x, you can disable it altogether, you can say 10x. And based on that is how much of the gains you'll get back in terms of quality. So effectively, this gives you very cost-effective scale with no quality trade-off. You choose how much of the mix you want to have for your own application. Now, when you combine all this compression work I talked about with the re-ranker I talked about in the previous section, you get this super interesting result. Turns out that the semantic ranker is so good that it can help recover quality when you've lost it in the previous layers, as long as you cast a wide net. So 2 concrete examples that we found in our data that's fascinating are, first, if you have a previous generation embeddings, say A.002, but maybe you have this huge vector index, you already built it, you don't want to build it again, no problem. Just enable the new semantic ranker, which, by the way, it'll be rolled out by default to anyone enabling semantic ranking. And you get almost all the quality back. You can see a difference here between 72.8 and 71.7. But you can see that there is a real loss on this side, but we recover all of it, or most of it, with the re-ranker. The other thing we can do, and it's surprising again that this works, but the numbers indicate that it works very well, is you can push harder on compression, lose more information during compression, and recover the quality during re-ranking. So before I talked about take 1/3 of the vectors. That was 1024 dimensions. In this test, we took 256, so 1/4 of that. So this is like 12 times smaller than the original vectors, and still did binary quantization on top, but then we used the re-ranker. Again, we recovered all of the precision back. Look at how badly the vector result alone suffered when we did this. Of course, we lost a lot of information, but most of it we could bring back with the re-ranker. So 2 interesting facts in addition to the independent components of compression and re-ranking is how well these compose together. All right, finally, we talked about quality, we talked about scale. I want to talk a little bit about meeting you where you are in the environment that you work on instead of having to find Azure Search in a particular place. If you use Azure regularly, of course, you'll find Azure AI Search in Azure. It's a first-class component of the platform. But we're also expanding it to show up in more and more places. Let me give you a few examples. First one, as we mentioned yesterday in the keynotes, now the GitHub models capability that we had shipped earlier now has support for RAG. So you can just out of the box in the GitHub experience, drop your own content, and you can do RAG right there in GitHub. No Azure account, no provisioning of anything, it'll just work. So this means you have out-of-the-box integration with the playground, so you can use it the same way you use models, but with your own data added. And it also means under the covers, we will provision an Azure AI Search service for every one of these accounts. So you get all the functionality we talked about in terms of full feature retrieval system, advanced RAG, all the re-ranking, all of these things we talked about. You get them right out of the box on a small service. So the RAG and GitHub models will be available very soon. And if you want to sign up, that URL over there will tell you to the sign-up form. And let me actually take a minute to show you what this looks like. So if you go to, actually, let me go back to the marketplace. So if you go to the models part of GitHub, you'll find the kind of model marketplace, and you can go into any of these models and try them out. I'm going to try GPT-4 Mini. When I go to the playground, I can chat with this model as usual, but now there is this new part here that says, hey, like, do you want to build an Azure Search index? So why don't we do that? I'm going to say upload files. I'm going to come here. I'm going to grab just a few so this goes quick. And I'm going to say upload so that these files go into GitHub. So GitHub has this, GitHub model has this interesting feature where you can compare side-by-side multiple models. We originally did this so that you can compare different LLMs. But you can actually use it for these scenarios too. So what I'll do is I'm going to add a system prompt. I'm going to say you help people with outdoors gear. And so now the parameters are synced, so I get the same in both sides. So what I'll do is I'll take one of these, and I'm going to kind of unsync it, so they are different. And the way it's different is one of them, I'm going to say, use the index for grounding. So now let's ask a question like, what's the X for tent? I copy this question and ask it here too. So this version, which is not grounded, it just speculated a little bit about the question. The word tent made it kind of guess a little bit about what it could be. The version on the right has grounding information. So it actually answered from the data I just put into my system. So the interesting thing is, so I guess we can close this one as not good. We'll keep the good one. So the interesting thing about this is I can play with this right here in GitHub models, and I can look at the interactions under the covers. I can see the grounding data, what was the back and forth between the two. But also, I can get the code. And the code for this, and I'll make it bigger in a second, the code for this includes the entire pattern, including calling the LLM, calling search, producing answers, and whatnot. And if you look a little bit right here, that's an Azure AI Search service. And it's yours to use. And the way you authenticate is with a GitHub personal access token. So the authentication model is GitHub's one. You can not even have an Azure account, but you can use this model. Once you're ready to use this, you can take this code, bring it to your favorite editor, maybe make a quick file here, make this bigger, not that big. And I'm going to save it. Let's say GitHub.python, and maybe adjust it a little bit. In this case, I'm going to just change the question. I'm going to ask again, what's the X for tent? And that's it. I can run it. So I'm going to say that. So that was the question I originally asked. It'll call the retrieval system. It'll call the LLM. And boom, here's the answer. And now you can start, like now I'm out of GitHub, I can customize this in my own application. And of course, once I'm ready for using a full-scale service in Azure, you can create an Azure service, change this URL to the URL that the Azure service gives you, and you're all set. The rest of the application will work as is. All right, so we talked about Azure, we talked about GitHub. Another place where you'll find now first-class support for AI search is in Copilot Studio. If you're building in Copilot Studio and you want to ground answers of Copilot Studio in Azure AI Search, taking advantage of Azure Search's ability to connect to all the data sources and do semantic ranking and whatnot, then this will work right out of the box. When you go to, actually, I'm going to go here. When you create an agent in Copilot Studio, there is an option to add knowledge. And as part of the list of knowledge sources, if you go to advanced, now you can see Azure AI Search there. And when you select it, you give it the URL to your service, your authentication information, and you're set. The agent in Copilot Studio knows when to choose to use information from this particular index, and it'll include it as part of the answers. And then finally, in terms of examples of this, of course, you can use Azure AI Search as a first-class citizen in the AI Foundry. when you use the Azure AI Agent service, you have the option to use knowledge tools to ground the information that the agents use to produce answers. Just like I showed you that you can go to, say, Copilot Studio and add a knowledge source for AI search, you can do a similar thing right here in the agent service, where you add a connection. You say the connection is of type AI search. And once it's set up, then we will directly pull information from the service. Now, of course, same thing. You get all the capability of AI search. You can do indexers, and you can do ranking and whatnot. And you manage it however you want. But then you get an integrated experience within the AI Foundry. So I mentioned at the beginning that we do the full life cycle. So I talked a lot about how we index and how we query and things like that. Now, of course, all these journeys start with the data source, like where is the data located, and how do you access it, how do you track changes. It's a lot of complexity on just managing data ingestion. And in AI search, we do this out of the box. And we do it for many data sources, including, whoops, I didn't mean to do that, including earlier this year, we announced native support for OneLake, and through OneLake with shortcuts to other data sources in other clouds. We also, of course, support blob storage, Azure Data Lake, SQL, Cosmos DB, and whatnot. Now, an interesting thing in terms of meeting you where you are in terms of scenarios is a lot of data is not even in the cloud. So we've been working together with the Azure storage team, the Azure blob storage team, on a work they're doing called storage connectors, with the goal of connecting all of enterprise data to AI. So that includes connecting not only data in Azure, but also data on premises and in other clouds, and still surface it through the traditional object storage API. So you get to use your applications as if this data was in Azure, as if it was just a blob storage API, even though the data is on-prem or in other clouds or in other services in Azure. So now you can unify how you access all this data and run your own experiments, or if you're using Azure AI Search, I just showed you how Azure AI Search can easily support blob storage. These two things work well together. So you can have a ton of data on-prem, don't even bother about moving it. Just create an index in the cloud, and then power your RAG application from that index. This is also in early preview, just like the GitHub one. So if you are interested in it, there's a link there. But also there is a session later this week by the team working on it. So if you're curious about this space, I recommend that you go check it out. So in terms of call to action, so first, main takeaway that I want you to think about is we are all in the business of building applications that people will love. We want to build applications people use, and they solve real problems. If a component of your system does not show a strong evaluations profile or has no evaluations at all, don't even bother. You don't know if it works. Nobody knows if it works. So evaluations are critical to the nature of these systems. For the search side and the retrieval system in general, we do the work for you and we publish it so you have the data. And I would encourage you to also do your own evaluations on your end-to-end stack to make sure that you understand the experience your end users will have. Second, I want to kind of reemphasize how the modern kind of ranking and compression techniques applied in Azure AI Search yield such a strong combination of high quality, cost effectiveness, and performance all in one box. So if you want to try the stuff that I talked about today, you can do it in Azure, you can do it in the agent service, you can do it in the Copilot Studio, and of course, you can do it in GitHub. And if you want to have read an in-depth analysis of not only the details of the numbers I showed for relevance, but also the methods applied to creating these evaluations, the nature of the data sets, and a ton more detail, the link at the bottom at aka.ms/AI search-QR has our most recent white paper in this space. And if you're curious about this, I can tell you this is a very fun read. So with that, we have a lot more going on this week when it comes to RAG and retrieval with Azure AI Search. Right after this at 10, I'll be in the Azure Unplugged space talking about the topic. We have 2 of our customers doing sessions together with us, sharing how they experienced this journey. We're also doing some work with our partner Llama Index on how to put these technologies together. In general, you'll find, also we have a session on GraphRag and how we'll connect GraphRag powered by Azure AI Search for retrieval. So in general, you'll see a broad spectrum of scenarios, both from us and from our customers, for how to go about building end-to-end RAG applications with Azure AI Search. And with that, really appreciate your time here. Hope this was useful, and hope you have a great rest of Ignite. Thank you.